Okay, so you are used to working with right triangles so far. We've been using things like sine, cosine, tangent, SOHCAHTOA, those relationships to calculate side lengths or angles within right triangles. But now we are going to start looking at situations where you actually don't have a right triangle. So you may have something that looks like this. So you might have a triangle that looks like that, or that looks like this, or looks like this. Okay. So when I look at this situation, I can generalize a particular relationship. Okay, this is where the sine law comes in, and I'm going to show you where the sine law actually comes from. So let's say that I have a triangle that looks like this. Okay, so this is not a right triangle. There are no 90-degree angles anywhere. But what I'm going to do is, within this triangle, I'm going to embed a right triangle, like an imaginary right triangle. So let's say, and then I just want you to think about how might you do that? How might you, could you make a cut in this triangle to create a right triangle? So the cut that I'm going to make is just like this. And maybe you're already thinking, hey, you could just slice it down the middle, right? So if I make a cut like this where the dotted line is, here's my right angle, and this is, I'm going to call this H. So this is the height of this guy. And like we did before, I'm going to make sure I label all the angles. I'll just say this is A, B, and C. And remember, opposite side lengths from the angle are like little a, little b, little c. Okay? And now what I'm going to do is I'm actually just going to use what I know about right triangles. That's SOHCAHTOA relationship. Okay, so I'm just going to use that. So let's say that I'm looking at angle A, okay, and I'm gonna use sine here to define the relationship between angle A and the side lengths. Well, if I was using sine, then I would say if I take the sine of angle A, it should equal my opposite length, which in this case is H, over my hypotenuse, which is C. And so that's me on the left-hand side of this triangle. That's where I see that right triangle. Okay, if I'm looking at it from the right-hand side, I would say that sine of angle C, which is over here, okay, that will be opposite. Hey, it's the same side length, right? It's still H. H is over in this, and on the right hand side, the hypotenuse length is A. Okay, so all I've done right now is I'm literally just using what we know about right triangles to just state this relationship. Nothing's really happened. This is like something we already understand. But now I want you to notice that because I've written this way, I can now rewrite this relationship in terms of angle A and that side length C. So I'm going to rewrite this as H equals. I'm going to multiply both sides by side length C. And then what I end up getting is I get C multiplied by the sine of angle A equals H. Okay, so I've literally just written an expression for that height, that H. And then I'm going to do the same thing with this guy. I'm going to rewrite this as, okay, I'm going to multiply both sides by A, multiply both sides by A. I get A times sine of angle C equals H. Now, I hope you're okay with how things are going so far. And hopefully none of this is confusing. It's pretty straightforward. Because this is now where you see, like, we start to see something interesting. If I look at the letter H, I actually have two relationships, or sorry, not two relationships. I have two expressions for the same length. I have H is equal to C times the sine of angle A. But then I'm also saying that this expression is equal to A times the sine of angle C. So this equals H, the left-hand side, and the right-hand side equals H. So that means that these two expressions must be equal to each other. And if they're equal to each other, now what I'm going to do is I'm actually just going to rewrite this as I'm going to divide this side by side length C. That means that this will cancel, okay? Whatever I do to the left-hand side, I got to do to the right-hand side. So I'm also going to divide this side by C as well, and there is no C for me to cancel. There's no side length C that I'm multiplying, so that guy has to stay, okay? So right now, my expression looks like this. It's sine of angle A equals A sine of angle C divided by C. And now I'm in the next step, what I'm going to do is I'm going to divide both sides by A. So I'm going to divide this side by A. Okay, so that will cancel. And I'm also going to divide this side by A. And so now I have sine of angle A over side length A equals the sine of angle C over side length C. Now, if you notice, if I take the sine of my side, or if I take the sine length of my angle, I'm dividing by its opposite side. So if I look at my original drawing, right, if I take a look, if I get rid of the H in here, let's redraw this down here so it's easier to see. So here it is. Looks A, B, C, and then remember this is little b, this is little a, and this is little c. Okay, let's take a look here. If you notice, when I take the sine of angle A right here and I divide it by its opposite side length, that is the same as if I take the sine of angle C and I also divide it by its opposite side length. This is referred to the sine law. This is what we call the sine law. It's this relationship of the angle and its opposite side. That ratio is equivalent to one of the other angles and its opposite side in the triangle. And in the same way that angle A and side length A have this relationship with angle C and side length C, the same thing is happening with angle B and little b as well. So I can actually extend this relationship and say, actually, also, if I took the sine of angle B and divided it by little b or side length B, it's actually also equal to these two ratios, like the sine of A over little a and the sine of angle C over little c. And this is what we call the sine law. And in the next video, you'll be able to see how we can solve triangles using this relationship.